Thank you very much. My talk today is related to the near-best polynomial approximation of harmonic functions. And I'm mainly interested in the uniform approximation, unlike the Carleman one discussed in the previous talk. So to give some motivation, I would like to start with the analytic case, with a uniform analytic approximation. So given the compact set K on the complex plane, we will denote by the capital A of K the set of continuous functions which are analytic in the interior points of this compact set. And by capital E sub n, we will be denoting the infimum of the uniform norm of the difference of f and the polynomial of the degree at most n. So this capital A of n will stand for this error in the best uniform approximation of our function from the class capital A of k. The classic result by Mergelin claims that this quantity will tend to 0. So these errors will go to 0 once we make sure that the complement of our compact set is connected. But our main interest is not to take a look at these errors at their behavior, but to consider a slightly different type of polynomials. And those polynomials, which are called as the near-best ones, are defined as follows. So these are polynomials little p sub n, so that the overall estimate on our compact set K is the best one up to some constant capital C, where this capital C is greater than 1 and it doesn't depend on n. So the main question is why to study the near-best approximants. One of the reasons is that although the best polynomials are best in the sense of the uniform approximation, but they have a really bad behavior of the zeros, and that's why it prevents them from the convenience of using them in the practical purposes. Therefore, the near-best, they behave much better in this sense, and people were trying to use them instead. Also, it turns out that these near-best approximants, they have a really nice property. They might improve the approximation of our function at the points in the interior of this set. And as an example, let's take a look at the following situation when the compact set is just a unit disk, the simplest one. In this case, if we take any function f from our class A of k, in this case, it's pretty easy to construct the sequence of polynomials so that this difference, the norm, will be bounded by this quantity. So capital C times the rate of the best approximation times z to the power n, where z is some point in the interior of our unit disk. So it means if I fix any compact subset of my unit disk, let's call it by E. In this case, I can find some constant, a little q. Let's do it again here. So I can find q, which is strictly less than 1, so that the uniform norm of the difference on this compact subset is bounded by the quantity which decays really fast. So we have the geometric rate of convergence on this compact subset. Therefore, we see that the overall we have the same, up to some constant, we have the best rate of approximation, but inside we have the very good improvement. And the very natural question here is that, is it still possible to expect this kind of behavior of near-best approximants for other sets different from the unit disks? And this question was studied by many people, and in particular by Shirokov, by Saf, Totik, and Maimesco. And they were investigating these questions when we still might expect the geometric improvement, or for which sets it's impossible. And for us in particular, the following two results by Saf and Totik are the most interesting ones. So the first is saying that if we have a set K, which is bounded by a simple closed analytic curve, then in that case, there is a constant capital C such that any function from our class A of K can be approximated with the following property. Overall, it's the best one up to some constant. And in the interior points, we have this improvement, which is the geometric rate of convergence. So the second line just is this geometric convergence written in this way, so that this lim sup of this ratio is strictly less than 1. So this is one of the results, and another one is more general one. So it states that if a compact set is connected and its complement also is connected, in this case they showed the existence of near best polynomials, and they gave the upper bound for the constant capital C. So they showed that this constant might be taken to be 2 and it cannot be improved. And also in the interior points, we have that this ratio is tending to 0. Here, unfortunately, they don't give the estimates for the possible rates of convergence in the interior. They just claim that we have some improvement. So based on these two results, we were asking the analogous questions, but for the harmonic functions. So if we take the same compact sets, let's say K, and we will consider the harmonic functions defined there, can we still construct the near best polynomials for such case?
Liudmyla.
Yes.
So the results, these results are very good, right? So you see, you give precise values 2 and 0 over there.
Yes. What I mean here is that they are claiming that here we have some improvement in the interior points. That's what the second line says, but they don't estimate how fast it goes.
So the basic example so the reader should have in mind is the Weierstrass approximation theory, like continuous so continuous function can be approximated by polynomials.
Yes, this is the very basic result, very fundamental one, but in sense that you can approximate the function continuous on the closed interval with an arbitrary rate of with an arbitrary prescribed error. Yes, but in that case, you don't. He doesn't give any relationship between the properties of the function and the possible rates of this convergence, except that he just assumes that function is continuous.
Okay, I see. Okay.
There are very numerous papers devoted to the questions. They are called the inverse and direct theorems by Bernstein, which, well, these theorems are exactly describing this relationship between the smoothness properties of the function and the possible rates of convergence of the uniform approximation of these functions by the polynomials.
Okay,
yes,
so
this is a separate.
Is there any good textbook that introduce this topic?
Yes, there are numerous books. If someone is interested, I can give reference later.
Okay, yeah.
It's really wide topic for this approximation, and people have studied it for tens of years since now. But my particular area is a near best approximation, so that I want to improve the approximation in the points where function is nice, where function is holomorphic, but I want to the overall approximation being almost optimal, so I don't lose this best rates overall on my set. That's the conditions I'm under when I'm talking about this type of problems.
Okay.
Yeah, so in this case, before stating the results, I need to introduce a few more notations. First of all, by capital H of k, we will call the family of functions which are continuous on k and harmonic in the interior points of k. And also now we need to introduce the error in the best uniform harmonic approximation, which is similar to the analytic case. So this is the infimum of this uniform norm of the difference over all these polynomials of degree up to n. So with these two definitions, now we are ready to state the first theorem. So in case the compact set K has the complement which is the John domain, in this case we are claiming that we can approximate this function so that overall the rates are the best ones, and in the interior points, in the compact subsets of the interior of K, we get the improvement in the form e to the power negative c times n to the power alpha. So again, the best one we would wish to have would be with alpha here being 1. But this theorem, it claims that we might get the improvement where alpha is some fixed number, not dependent on n, which is between 0 and 1. So with this case, as a particular case of this theorem, with a slight improvement of the proof we're using here, we can actually get the analog of the situation for the unit disk for harmonic functions. So this simple corollary claims that if we have a function now from the class h of dr, in this case we construct the sequence of polynomials so that overall the rates are almost optimal ones, and in the interior points we have this improvement, but now it's a bit more specified. So here we have the constant c times n times some quantity d of z, where d of z is the distance from our point to the boundary of the disk. And unlike in the previous case, this constant c will not depend on the compact subsets, which we are considering. So this is a slightly improved version of the previous theorem, but with the help of this corollary, we get the analog, complete analog for the analytic case on the unit disks. And the second theorem concerns the case when the compact set is bounded by a simple closed analytic curve. So in this case, what we are getting is the analog of the self-syntactic result. We are seeing that in the interior points, we get the geometric rate of convergence of our polynomials. And the next, I would like to outline the proof of the first theorem and mention the main tools used for the second one. So the main idea here with the first case is to take a look at our function u, take the sequence of the best approximants, which we are calling by p sub n comma delta, and then consider a new family, which is called here by v sub n. As you can see, this ratio here is uniformly bounded by 1 on the compact set K. So these functions can be continued on the whole space with the norm being preserved. And well, without loss of generality, we can simply think that all these functions, they have some bounded support. And then with these functions, we will do the following thing. So we will introduce the smoothing kernel, capital A sub zeta, and then we will take a look at the new family of functions. So we will try to approximate those functions which are having the nice expressions. Therefore, we modify the original functions v sub n. So we introduce these v tildes that are just smoothed functions v sub n. And then we notice a few very useful properties that these functions possess. First of all, they are pretty close to the functions v sub n in the sense that this difference is uniformly bounded by some constant for all points on the complex plane. Also, the Laplacian of this family is uniformly bounded by by constant over delta squared. And the last thing that is useful for us is that these functions, they are actually coinciding with the v sub n, with the original ones, once we are pretty far from the boundary of the set, once we step inside of k a little bit. So with these properties now, we can use the Green's formula, which allows us to get this representation of these functions v tildes. And why is it useful? Because we can see that the function that depends on z under the integral is this logarithm only. And therefore, our main goal here is to approximate this kernel, this logarithmic kernel, by polynomials, and this is the main idea of this proof. Therefore, the next step is to try and see what kind of polynomials we can use in order to approximate this kind of functions here. And for convenience, it's much better, much more convenient to approximate the logarithm of this ratio instead, where zeta 0 now is some point which is far enough from the compact set. So to approximate this logarithm, we will use the lemma proved by Andreevsky. So he showed that for such a function, we can construct the harmonic polynomial kernel so that the difference is bounded by this quantity up to some constant. And by polynomial kernel, what I mean the function here, which is a polynomial in the variable z, and which has the coefficients dependent on zeta, which are integrable. So that's what is harmonic polynomial kernel here. And basically, these two terms here will be used for two different kind of situations. One will be playing the major role when estimating for points which are close to z. Another term will be a major one when we will estimate at regions which are points which are far enough from the point z. So with this lemma, we need to have some improvements, because Andreevsky was using this to show the results for the estimates for the uniform approximation overall on the set. I need the improvements in the interior points. Therefore, I needed to modify this approximating polynomial kernels so that in the interior, it gives me the desired estimate. Overall, it's still the same estimate, but I have the slight improvement inside. And using this lemma right now, what we need to do is take a look at the other sequence of functions, which we are calling by g sub n, where compared to the v tildes, now we have the logarithm of the ratio instead of the just logarithm of zeta minus z. So that if now we take a look at this difference, the difference will be a function which is harmonic in some fixed neighborhood of k. And the famous celebrated theorem of Bernstein-Walsh claims that in this case, such functions which are harmonic on a compact set, they can be approximated with the geometric rate of convergence. Therefore, this difference is not hard to approximate. We kind of get the approximation automatically. And what we are left to approximate is the functions g sub n of z themselves. Therefore, to approximate this family of functions g sub n, we introduce the polynomials h sub n here. And for the approximation, we use the same expression, but instead of having the logarithmic kernel, we implement this polynomials t sub n from the lemma. And the last step in this procedure is to look at the difference and estimate the difference between g and h functions. So by splitting the area of integration, we can see that basically these two functions, the difference is bounded uniformly by some constant. And if we take a look at the interior point of the compact set, so here E is some compact subset of the interior. In that case, we can get the improvement in the form e to the power negative constant times n to the power alpha, which we were claiming initially. So that's the idea of the proof of the first theorem, and now I just want to briefly outline what is the idea with the second one. Unlike the first one, the first theorem is constructive one. The second one does not give us the polynomials, does not show the way to construct these polynomials, but it heavily uses the results of the first theorem. So I recall you that here we are on the conditions that our compact set is bounded by the analytic simple curve. And in order to start approximation on this type of compact sets, we need to take a look at the conformal mapping. So we will map conformally the exterior of this compact set onto the exterior of the disks of some radius capital R. And this capital R is chosen so that function phi is normalized as follows. At the infinity, it's equal to infinity, and the derivative at infinity is equal to 1. Since our set is bounded by this analytic curve, in this case, this conformal mapping can be continued slightly inside of this compact set K. So I have a picture somewhere. So the function phi is mapping the exterior of this compact set K onto the exterior of this disk of radius capital R. And we are extending our mapping slightly into the interior of this compact set. Why we need this? Well, this mapping simply helps us to reduce the problem of approximation on the compact set to the problem of approximating of functions which are harmonic on the disks. And on the disks, due to the first theorem, we know what to do, what kind of polynomials to take. So to help to reach this goal, we need to introduce so-called the harmonic Faber operators. So those operators will map our functions harmonic on the compact set onto the functions which are harmonic on the disks. And well, in order to be able to estimate the difference on the compact subsets, we need to deal with the family of the nested subsets of this compact set K. So this subsets we call by K sub rho, where rho will be changing from some little r to this capital R. And we will consider the family of the harmonic Faber operators on each of these subsets. So I will just mention here that this so-called harmonic Faber operator, they possess a few really useful properties that we need to use for our proofs. And one of these properties is the uniform boundness of these operators. And another one is that this operator is actually the topological isomorphism, which means the inverse operator, it exists and is also bounded. So those two results, one by Jürgen Müller and another by Marvin Müller, those results were proven pretty recently, although the Faber operator, which is known for a few decades, it was discovered pretty long time ago, but the harmonic one was not considered for a while since then. So we use these two properties in order to show that indeed for a compact subsets of our compact set K, we indeed have the geometric rate of convergence of our near best polynomials. So that's the idea with the second theorem. And well, I think I ran out of time, so it's better to stop here. So thank you very much.
You can continue until you finish.
I can, well, the rest of the slides is just the proof of this statement, but I just wanted to outline these major points of this proof. without
I see.
going much into the details.
So you're using the results by Miller and by the results from those two papers to run your argument.
Yes, I needed the boundness of these Faber operators. Yes.